Good evening and welcome, everybody. It's Obi-Wan, Paz 4, and Simplex Pachinko. We're going to be working on some math communication for Monday. Tonight, The Story of Geometry Told by Coins by Heinrich Fuchs. So, see how things are going. Right. So, Department of Mathematics and Statistics, Brock University, Ontario, Canada. In 3 articles published in CNJ in 2012 and 2016, updated authors' versions available on arXiv, we discuss some links between mathematical sciences, coin minting, and numismatics. The article is a continuation of long overdue of this cycle. It tells the story of a selected important developments in the history of geometry using modern commemorative coins as background and illustration. Geometry is one of the oldest branches of mathematics. Nonsense. It is one of the oldest formalized branches of mathematics. Mathematics itself goes back multiple thousands of years beyond when geometry was created and dealt with like number theory and applied mathematics way before. Well, okay. I guess it also informally did help out a bunch of. Yeah, there we go. Okay. Never mind. Third of the way down. I got it. I suppose. It studies properties of space and properties of objects, i.e. figures in space, using concepts such as distance, shape, size. Almost all ancient civilizations developed some sort of geometrical concepts, especially those concerning the measurement of lengths, areas, and volumes. Mesopotamian and Egyptian civilizations are believed to be the first cultures where such concepts appeared, but the ancient Greek mathematicians are credited to be the true originators of rigorous geometric procedures and were the first to use deductive reasoning to solve geometric problems. In the popular mind, Greek geometry is often associated with Pythagoras and his famous theorem of right triangles, discussed in 3. We will not repeat it here, only adding that a new coin commemorating Pythagoras appeared since the publication of 3, namely the €10 silver coin issued in 2013 by the Bank of Greece under the program Greek Culture Mathematicians. Picard-Lindelöf. Pythagoras o Samios. I don't know what character that is. It should be uppercase. Yeah. Not seeing a good candidate for that. It's a little weird. Jonas 9. Demo Democratia. Yeah, I think so. In spite of Pythagoras's popularity among students of elementary geometry, historians of mathematics tend to emphasize the achievements and influence of other ancient Greek mathematicians, often referred to as the Big Three, namely Euclid, Archimedes of Syracuse, and Apollonius of Perga. Euclid is considered to be the father of geometry, famous for the book The Elements, and which is the most successful textbook of all time. In terms of the number of editions, it is second only to the Bible, and has been used as a textbook until the early 20th century. In the English language alone, there are nearly 20 different translations. Again, this is where Euclidia gets its name from. So, oh. Boo. Alright. I won't log in, I suppose. It is therefore somewhat surprising that Euclid had to wait nearly 23 centuries to be commemorated on a coin. This happened in 2023 when the National Bank of Greece issued a silver €10 featuring the portrait of Euclid on the obverse, designed by Georgios Stamatopoulos. The portrait is obviously a product of the artist's imagination, since no image of Euclid survived to our times. Yeah, well. The reverse is a mosaic of various geometrical figures whose properties are investigated in the elements, such as lines, circles, ellipses, and polygons. An observant reader will notice that spirals are present too. This is a bit of an anachronism, as there is no mention of spirals in Euclid's works. Yeah, well. Nevertheless, the next of the big three, Archimedes, studied spirals in great details. He, just like Euclid, had to wait until 2015 to be featured on a coin. There is also a silver-proof coin, part of the same Bank of Greece series as Euclid's coin, designed by the same engraver. Archimedes, one of the greatest mathematicians in history, and arguably better engineer than mathematician, but yeah, I'm not gonna be too picky. Developed ingenious methods for calculating areas and volumes of geometric figures, including the circle, ellipse, and sphere, as well as the paraboloid and hyperboloid of revolution. He invented the method of exhaustion for this purpose, anticipating modern infinitesimal calculus developed in the late 17th century, somewhat. The bust of Archimedes on the aforementioned coin is shown in the background of a system of compound pulleys, one of his numerous inventions, simple machine known as block and tackle. The circles on the reverse, with one of them playing the role of 0 in the €10 inscription, likely pay homage to the alleged last words of Archimedes, "Noli turbare circulos meos," do not disturb my circles. According to the Roman writer Valerius Maximus, Archimedes uttered these words, slightly differently phrased, to a Roman soldier who came to kill him during the siege of Syracuse in 212 BCE, referring to a drawing of geometric figures which Archimedes had outlined in the sand shortly before the deadly encounter. Almost certainly apocryphal, but nonetheless. Thales. I think that's Thales. The third of the big three, Apollonius of Perga, is known for his work in the so-called conic sections, curves obtained from the... That's interesting. There we go. Thales of Miletus. Yep. interesting. I think this says Milesios. Or Milesios. So it is not Miletos as written there. Those are also not in order, so that slightly bothers me, but that's all right. Apollonius of Perga is known for his work on the so-called conic sections, curves obtained from the cone's surface intersecting a plane. These curves are known today as Apollonius named them, namely ellipse, parabola, and hyperbola. Apollonius does not have his own coin yet, but one can hope that this changes in the near future, given that the Bank of Greece continues the program Greek Culture Mathematicians. In 2024, another coin belonging to this program has been produced, this time Thales of Miletos. Everyone who is fortunate enough to be exposed to traditional geometry instruction in high school certainly remembers his name, thanks to the basic proportionality theorem, commonly known as Thales' theorem. If BC, DE are parallel, then the proportions of DE to BC, AE to AC, and AD to AB should all be identical. No writings of Thales survive, but Thales' theorem appears in the first book of Euclid's Elements as the 26th proposition. And here is my gripe. The rather enigmatic reverse of Thales' coin is, in my opinion, a missed opportunity. The illustration of the basic proportionality theorem almost begs to be included. As we mentioned at the beginning, other ancient civilizations also developed geometric ideas and made progress in expanding geometric knowledge. The Chinese civilization was certainly one of them. Zhu Chongxi was one of the most prominent Chinese mathematicians of late antiquity, whose greatest achievement was calculating pi to 8-digit precision. He found the upper and lower bounds on the exact value, 3.1415926 and 3.1415927. He gave a rational approximation, 355 over 113. The 5 yuan silver coin, issued in 1986 by the People's Republic of China, presents a full-body portrait of Zhu Zhongxi in the background of the hammer mill, one of his mechanical inventions. On the top left, we see the polygon inscribed in a circle. Ta-da! In deriving his results regarding pi, Zhu Zhongxi approximated the circle with n-sided polygons using increasing values of n. I believe that is also what Archimedes did. It is not known exactly how he obtained these interval of bounds on pi. But some authors conjectured that he started with a hexagon and then doubled the number of sides, its sides many times, obtaining polygons with 12, 24, 48 sides, etc. Internet sources such as Wikipedia authoritatively claim that he ended up with a polygon of 3 times 2 to the 12th sides, but there are valid reasons to doubt this. Historians of mathematics suspect that he actually started with a square, doubling the number of sides until he obtained a polygon with 2 to the 15th sides. Fortunately, the designer of the coin did not have access to Wikipedia in 1986, thus leaned toward the more probable hypothesis showing an octagon on the coin. This corresponds to the first step in the approximation, 4 sides of a square after doubling, result being 8. Coming back to Greek mathematicians, it is often said that after the death of Archimedes, geometry suffered a decline. Indeed, Pappus of Alexandria and commentator on Euclid's Elements, Proclus Lysius, are the only Greek names in late antiquity worth mentioning as long as abstract geometry is concerned. Whoa. Nevertheless, it is fair to say that practical geometry enjoyed a much better fate. Claudius Ptolemy produced his seminal astronomical treatise known as Almagest where he described his geocentric model of the universe based solely on geometric principles. He also wrote a book known as Geographia, where he explained how to draw maps using geographical coordinates, similar to what we use today. Well, my goodness, René Descartes would have a fit. I'm sure they used about the same stuff anyway. In 1992, Cuba issued a 10 peso silver coin honoring Ptolemy, together with a 15th century mapmaker and a mathematician, Paolo Toscanelli. The reason for including them both is because Toscanelli used Ptolemy's geographic information from Geographia and came up with the idea of sailing west to reach Asia by covering a distance of only 6,500 miles. He prepared a map illustrating his idea. Columbus had Toscanelli's map, and it convinced him to try to find a direct water route from Europe to Asia. Modern rendering of the map, the original is lost, is featured on the Cuban coin, which commemorates the 500th anniversary of Columbus's voyage. One can see from this map that Cipango, i.e. Japan, is separated from Europe and Africa by the Mare Oceanum, Ocean Sea. We'll return to the subject of map making shortly, but for now let us continue the discussion of developments in geometry in a chronological way. In the Middle Ages, not much happened in abstract geometry in Europe, although in the late Middle Ages, practical geometry flourished again. The monumental Gothic cathedrals of Europe are a living testament of the skills of medieval architects who used various geometric methods to design, lay out, and build these magnificent structures, not creatures. That's different. Seriously. Not everybody's caught up there, I guess. How's it going, Zach? Hope everything's going well tonight. Got a late start, but, you know, it'll be alright. Looks like we'll be getting through this paper at least. It's a very easy read and not a whole lot of things that we have to, let's say, prove or try to convince myself are 100% true. We're going to get historical representations, which are going to be as close as we can imagine that they would be. At the beginning of the 15th century, we encounter another crucial development in practical geometry. Filippo Brunelleschi, featured on the 1,000 lira coin of San Marino from 1977, 400th anniversary of his birth, was an Italian architect and designer. In the years 1415 to 1420, he conducted a series of experiments which led him to the discovery of the linear perspective, a method of representing three-dimensional objects on two-dimensional canvas, producing the illusion of depth. He is credited to be the first person to precisely describe the principles of linear perspective. San Marino coin shows the obverse group of people raised on a platform or scaffolding, presumably representing the architect Brunelleschi discussing something with builders. The beams perpendicular to the plane of the coinage perpendicular to the plane of the coin converge to a point located outside of the coin. Following the rules of linear perspective, although with a bit of fisheye distortion added to harmonize with the circular shape of the coin. So yeah, we got these right here, or that way. Up top, we got a dome-like structure. In the 1470s, an Italian painter, Piero della Francesca, developed further Brunelleschi's ideas and produced an influential work titled De Prospectiva Pingdendi on the perspective of painting. Inspired by the work of Euclid, Piero della Francesca described mathematical principles of perspective and explained how to create perspective with colors. The Italian 500 lira coin from 1992 shows the portrait of della Francesca on the obverse and one of his most famous frescoes, The Resurrection, on the reverse. While the composition on the Resurrection is based on some geometric principles on the right, the use of perspective is better illustrated with della Francesca's The Flagellation of Christ below here. Wait, hang on. Ah, that one. Yep. Where a number of straight lines clearly converge to a single point. After della Francesca, at the beginning of the 16th century, Franciscan friar Luca Pacioli further advanced the theory of perspective in his book Divina Proporzione. The book discusses the notion of proportions in visual arts in the context of perspective with applications to architecture. The 500 lira coin from 1994 features his portrait circumscribed by the inscription 1494 Luca Pacioli 1994. The year 1494 represents the publication date of his other influential work, Summa de Arithmetica, which, among other things, contains the first published description of the double-entry bookkeeping system. The work earned him the title of Father of Accounting. Yay! After discussing the developments of practical geometry, let us turn to more abstract problems. In the first half of the 17th century, an important development in abstract geometry emerged, which could be described as the marriage of geometry and algebra, mainly due to René Descartes, who formulated the principles of analytic geometry, or, in other words, the study of geometry using the coordinate system. Today, analytic geometry is often called Cartesian geometry, and Descartes is credited as its sole founder. I mean, his portrait is not necessarily a flattering one, but, like, that looks like a particularly bad portrait of him. Descartes is credited as its sole founder, although it is worth stressing that Pierre de Fermat also contributed to the subject. The coin of France, issued in 1991, un cent francs, shows the head of Descartes with his hair smoothly transitioning into books on the left and a scroll on the right. Somewhat more related to geometry is the 50 lira coin of San Marino from 1996 with the bust of Descartes inscribed within Cartesian coordinates. See, like, that one's okay. This one, though, it's just, whew. Moving on, 18th and 19th centuries, we encounter the towering figure of Carl Friedrich Gauss. Yeah. One of the most influential mathematicians in the history of mathematics. Yeah. Often referred to as the Prince of Mathematicians. This is not a place to describe his countless contributions and various branches of mathematics. Thus, we will only mention geometry. Before we do this, let us mention that in 1977, on the 200th anniversary of Gauss's birth, 2 competing coins were issued by the then 2 distinct German states, German Democratic Republic and Federal Republic of Germany. The East German coin had the denomination of 20 marks, Eastern obviously, and carried the graph of the Gaussian curve. Well-known probability distribution function widely used in statistics, also known as the bell curve. Very well chosen symbol of Gauss's contributions to mathematics, as it is instantly recognizable and entrenched in popular culture. It's true. The West German coin with 5 Deutsche Mark denomination is more typical commemorative coin with the portrait of Gauss inspired by the well-known painting by Christian Albrecht Jensen from 1840, with Gauss wearing his characteristic hat. Although in the 1970s the black market exchange rate was 5 to 10 Eastern marks to 1 Deutsche Mark, making the 5 Deutsche Mark coin more valuable than the 20 Eastern Mark coin of DDR. Today, the East German coin reaches much higher prices on the collector market than its West German counterpart. Of course, this mainly reflects the difference in mintage, 55,000 versus 1 million. Gauss is considered one of the discoverers of non-Euclidean geometry, and more about this later. Yet Gauss also initiated differential geometry of surfaces, which is different from Cartesian geometry because it studies surfaces from a point of view of an internal observer, constrained to move on the surface, as if it were two-dimensional. One of Gauss's greatest achievements in this area was his Theorema Egregium, remarkable theorem, which informally says that the curvature of a surface can be determined entirely by measuring angles and distances on the surface itself. One of the consequences of this theorem is that a sphere's surface cannot be represented on a plane without distortion. Thus, one cannot produce a map of a significant area of the Earth which would be free of distortion. Consider, for example, a frequently used map projection known as Mercator, invented by Flemish geographer Gerardus Mercator, featured on the 5 mark silver German coin of 1969. A. Oh, Gerhard, yeah. Oh, but right. This one's Flemish, and therefore used Latin. Mercator projection has some excellent properties, preserving local directions and shapes, yet it also inflates the size of objects far from the equator, as seen in the whole Greenland debacle. No, probably not, but my goodness, it's the size of the entire United States. This is illustrated in the sample map on the right. Red circles in reality have the same area, yet on this map they have different sizes. Gauss demonstrated that every projection, no matter how clever, will always result in some deformation like this. As is already mentioned, the name of Gauss is often linked to another important development in geometry. In order to describe it, some preliminary remarks are needed. In the Elements, Euclid gave 5 postulates for planar geometry. Postulates or axioms are statements which are believed to be obvious and require no proof. The first 4 of them assume that it is always possible, 1, to draw a straight line from any point to any point, 2, to extend a finite linear segment continuously in a straight line, 3, to draw a circle with any center and a radius, and that 4, all right angles are equal to one another. Not quite as put as eloquently as that, but most of them are pretty close. The 5th postulate, called the parallel postulate, was far more complicated and not immediately obvious. Namely, if a straight line falling on 2 straight lines make the interior angles on the same side less than 2 right angles, the 2 straight lines, if produced indefinitely, meet on that side on which the angles are less than 2 right angles. More accurately, the 5th postulate's purpose, and in fact what it's really doing, is defining the curvature of the space on which you live. So the fifth postulate is absolutely necessary and must be an assumption and cannot be actually proven, because if you just use the first four, there's no guarantee that you are doing work on a flat plane, or you might be doing work on a sphere or a spherical shape, or you might be doing work on a hyperbola or hyperbolic shape. And the three curvatures, hyperbolic, planar, and spherical, end up producing our three geometries, which are independent of each other and which are wholly necessary to define separately and individually. So, locally, everything's going to look planar. Right? If you shrink down sufficiently far, every surface will eventually look planar, provided it isn't singular at whatever location you're at. Might be tilted, but it'll look planar still. Today, we usually state the fifth postulate in the equivalent form given by John Playfair. In a plane, given a line and a point not on it, at most one line parallel to the given line can be drawn through that point. Because the fifth postulate is not self-evident, for over 2,000 years mathematicians tried to prove that postulate using the first four. In the 19th century, it finally turned out that such efforts were futile because the parallel postulate is independent of the remaining four. One can therefore construct a self-consistent version of geometry either with or without the fifth postulate, meaning that there is no one geometry but many geometries. This remarkable and truly groundbreaking result has been discovered as it happens independently and nearly simultaneously by two people, Hungarian mathematician János Bolyai and Russian mathematician Nikolai Ivanovich Lobachevsky. Both Russia and Hungary commemorated their fellow countrymen with coins. I do take exception to a couple little things in here. First of all, it is clearly evident that Euclid knew that spheres worked and that his particular mathematics, his particular geometry, did not work on a sphere. And so he came up with that particular postulate, I am sure, to make sure that people were not working on a globe. This reminds you of XKCD? Which part? There are so many XKCDs. It's great. The Russian 1 ruble copper-nickel coin commemorates the 200th anniversary of Lobachevsky's birthday. It is one of the first commemorative coins minted in 1992 by the Russian Federation after the dissolution of the Soviet Union, bearing on the obverse the new inscription Bank of Russia in place of the former CCCP. The reverse features a half-body portrait of Lobachevsky looking very sullen. There's a wiki explaining every single XKCD. Yes, I have seen that. The 200th anniversary of the birth of János Bolyai happened 10 years later in 2002, and Hungary followed suit by commemorating this event with the 3,000 forint silver coin. Bolyai published his work on non-Euclidean geometry in 1831 as an appendix of a book authored by his father. The reverse carries the full title of his work in Latin, Appendix Scientiam Spatii Absolute Verum Exhibens a Veritate aut Falsitate Axiomatis 11. Euclidiae a priori haud unquam decidenda independentum adjecta ad casum falsitatis quadratura circuli geometrica. I mean, it's not. It may not be like specifically Wikipedia, yeah, but it's. Wait, what were you looking at? No, no. We have a raiding party from Famished. How you doing, Famished? And thank you so much for testing out the brand new, testing out our brand new raid message. So, hope y'all are having fun. Just been chilling, felt like streaming you working, so yeah. Hey, it works. Always welcome. English title translates as Appendix, the absolute true science of space exhibited, independently of the 11th Euclidean axiom that can never be decided a priori being true or false. For the case of being false, the geometric quadrature of the circle is supplemented. The averse shows an exact copy of one of those figures from the appendix, namely figure 10 reproduced on the left, seen here on that particular coin. Bolii, appendix, etc., etc., etc. Also true. During his lifetime, Bolii had not received the recognition he deserved. A copy of the appendix work was sent to Gauss by Farkas Bolii, father of János. Gauss wrote in response that he was unable to praise János's work because that would be as if he had praised himself, as he had discovered the main results some years before, but never published them. Just like Newton, I swear. This was a devastating blow to Bolii, even though Gauss had no claim to priority since he had never published his alleged findings. Furthermore, after the death of Gauss, no written proof of the aforementioned statement was found in any of his papers. The discoveries of Bolii and Lobachevsky fell into obscurity after the publication and were almost entirely forgotten until 1860s, when the work of Bernhard Riemann on differential geometry sparked a new wave of interest in non-Euclidean geometry. Really too bad. Riemann posed a very general recipe for creating geometry in arbitrary space. His recipe requires only the ability to measure distances between points, so that any 2 points you can talk about the shortest path between them, and the ability to measure angles between intersecting curves that cross. The notion of distance allows us to compute a quantity known as curvature, which in the space with Euclidean geometry is exactly 0 everywhere. Although Riemann did not explicitly name them as such, the geometries of Bolii and Lobachevsky are special cases of Riemann geometry corresponding to constant negative curvature. Today, such geometries are known as Bolii-Lobachevsky or hyperbolic geometries. After the second half of the 19th century, geometry experienced further intense growth. In addition to differential geometry, many new branches appeared, including algebraic, finite, and computational geometries. Some of these fields are very new, and we'll have to wait a bit until we see the commemoration of their founders on coins. The next opportunity, however, is very close. In 2026, we will celebrate the 200th anniversary of the birth of Bernhard Riemann. One can only hope that his contributions to mathematics, including geometry, are also honored with a beautiful coin. Twould be nice. Anyway, yeah, I do have to say I really like this one, the Gauss coin from DDR. Deutsche Demokratische Republik. So, anybody who didn't know, that's East Germany. We ended up going there in our Berlin trip. So it was very interesting. We got to go into the Parliament building. We looked down through like the touristy area, and they have a it's very cool like dynamic building slash sculpture that sits atop the parliamentary, like the floor of their parliament. What would be essentially the Senate floor of the United States Senate, but Germany. There are little mirrors on every surface of this thing, which follow the sun as it goes through the day and reflects as much sunlight as it can into the Parliament chamber. So it's pretty cool. Works out very well, and if they were to use solar panels, it would also increase their solar collection. It'd be pretty awesome. Wouldn't quite reflect as much light, but Where is it? Where is it? Deutsche Bundestag. That's it. City center. Number 2. Oh, there it is. Oh, okay. Reichstag building is the actual parliament building. Yep, that's it. It's very cool. Here, let me pull it up. Yeah, our Senate building does not look this cool. So there is a spiral that goes all the way around this whole thing, and you can take a walking tour, and you've got your choice of language. So you put that over your ear, and then you're just doing this whole tour, audio walking tour, and as you get close to one of the like items, it'll just basically ping your device and tell it, hey, you're going to be doing this particular one now. And so it like radio tags, sends a little radio ping to your device to activate whatever piece of the walking tour it is that you're at. This right here is a solar shield that does dampen some of the light. and then the rest of it goes on to these mirrors here, and they will turn based on the time of year and the time of day, how much light they want to collect in the building, so that the sunlight will get filtered through the filter, hit the mirrors here, and then get fed down into the actual Parliament chamber in the Reichstag building. Yeah. Currently houses German Parliament and was the seat of the Weimar Republic government until it was seized by the Nazis in 1933. Yeah, I highly recommend, if you're gonna go to Berlin, definitely go see the sites. The fact that they let you into like their parliament, you're literally standing over the top of their lawmakers. May not be open every single day, but still. Right? 8 a.m. to 10 p.m. every single day. Reichstag. Yeah. I mean, you look at that. Number 3 of almost 2,000 things to do in Berlin. So yeah, if you are going to Berlin, definitely, this says like, you know, the duration is going to be 2 to 3 hours. You do have to sign up ahead of time, and you do have to, I want to say you submit your documents for security clearance ahead of time. Like you send your passport number over, and they're just like, let's make sure that they don't have any Interpol activity. And you probably don't want to bring a giant backpack either. I was wearing a day pack, and they looked at me funny, but it was okay. Add it to your list of places? Nice. For anybody who missed it, this past Thursday I did a TTRPG planning session for my TitansGrave, the Ashes of Volcana stuff, and we didn't get very far, but nonetheless, it was like, you know, here's a whole bunch of ideas that I have, and some of the basic stuff is in here following what's in the book, and some of the like further things to look into, I just basically made them up. Yep. And this island here, this island continent, we also did a quick calculation based on the number of degrees that this is going both in longitude and latitude, and then I assumed that Volcana is roughly the same size-ish as Earth, therefore this ends up being something about 2,000 miles square around here and down here. Or, well, 2,000 miles each side. Kilometers. Kilometers. 2,000 kilometers. God. Yeah, I really like these coins. That's really nice. Oops. Don't do that. Alright. Last time we were discussing the Picard-Lindelöf argument and the Banach-Caccioppoli contraction mapping principle by Alexander Bufetov and Ilya Zavolikin. Okay, so we talked about Ivan Grigorovich Georgievich Petrovsky in 1939 gives 3 proofs of the existence and uniqueness of solutions for ordinary differential equations. So we did talk a little bit about that and talked about the, like, what are the existence and uniqueness ideas that we have now, which for the most part, let's see. The existence of a solution is guaranteed as long as there isn't a singular point, as long as it's defined on whatever intervals you feel like. And then also, the uniqueness is guaranteed as long as the function doesn't become singular and its derivative doesn't become singular, I believe, for the 2 bits that we needed. Wait, what is that? No, that's Springer. I swear I had, what's his name? Trench's book open. Elementary differential equations. That's the one. Boo. Disgusted. Okay, they want me to download it. I have it. I have it in my actual folder up here. It's very not helpful. Documents, math, DE, nope, books. Nope. Well, I guess it should be differential equations, but... Yep, there we go. Trench, elementary differential equations, with boundary value problems or not. Let's go with. Why not? Okay. Control F. Existence. Okay, page 55. Existence and uniqueness of solutions in nonlinear equations. Right. If f is continuous on O... No, that's right. Okay. If f is continuous on an open rectangle, so AB to CD, A to B and C to D, that contains an initial point x0, y0, then the initial value problem y prime equals f of xy, where y of x sub 0 equals y sub 0, has at least one solution on some open interval of a to b that will contain x0. So as long as we're in a continuous region, as long as our function is continuous, then we're good. We definitely will have at least one solution. If both f and the partial derivative of f with respect to y are continuous on the reals, then that function has a unique solution, or sorry, the differential equation has a unique solution on some open subinterval of a b that contains x sub 0. So that's all good. So here, this is going a bit further. Existence is proved by the Euler method of piecewise linear approximation of solutions. Existence of 2 distinct solutions with the same initial condition is then shown to contradict the Lipschitz condition. I don't know what that is. If anyone does know what the Lipschitz condition is, then Lipschitz condition of functions. Lipschitz continuity. Perfect. Named after German mathematician Rudolf Lipschitz. Strong form of uniform continuity for functions. Intuitively, a Lipschitz continuous function is limited on how fast it can change. There exists a real number such that for every pair of points on the graph of this function, the absolute value of its slope is not greater than some real number. The smallest such bound is called the Lipschitz constant of the function. Okay. Hey, University of Chicago. Nice. I had a few friends who went there. Existence and uniqueness are proved using Banach-Caccioppoli contraction mapping principle, to which I.G. Petrovsky himself gives the name Caccioppoli-Tikhonov theorem. Its first proof, Petrovsky used compactness argument based on Arzelà-Ascoli theorem, which therefore only yields the existence of solutions, does not give any approximation to the solutions. Note, however, that the Euler method used in the proof of Peano existence theorem can be shown to yield a sequence of piecewise linear approximations converging at a polynomial rate. The contraction mapping principle yields an exponential rate. Picard-Lindelöf argument yields an estimate of the form O of alpha to the n over n factorial for the uniform norm of difference between the nth Picard approximation of the solution. This is not going to work very well for me. I think I already made that assessment last week. But ads are going to start to play. So we're going to go downstairs, grab a snack, drop this downstairs. Thank you, everybody, for coming. We'll be right back. 3 minutes. Thank you so much. Welcome back. Alright. Those of you who are new, welcome. We do a bit of martial arts. So, tonight is, can be a karate night. Just doing some quick warm-ups that I learned in Tai Chi. So we try to basically just let the arms swing, and then we're adding energy into them by twisting the hips. And in fact, you can just do it by twisting the hips, not actually like dropping in. But that's another way to do it, is you tuck into what's called the inguinal crease, which is that part right in here between your thighs and your abdomen. You just kind of like twist a little bit at the hips and then drop into it, and it adds a lot more power. It was what was originally thought of as the location where you store and get all of your chi energy from, but nowadays we think of it as mostly a biomechanical process rather than spiritual. Right. I can also swing side to side. And again, gravity assist. Hope y'all are having a great day. Today was a pretty uneventful Monday. Just had to go grocery shopping. And tomorrow we got a bit of I gotta have a discussion with the president of our parents and friends group. Basically PTA. I'm the treasurer, so I gotta have a discussion with the president about the current state of affairs of our accounts and whether or not the accountant did all of his stuff right, which I'm pretty sure he did, so I think we're good. I think he said there was a bit of a budget shortfall, but that's kind of to be expected this year because we had a bunch of big ticket items that went through, so we just didn't quite plan for everything we had to get in there. But if I took his meaning to be correct, all of our monies were accounted for, so. And this is also a really important thing. If you are over the age of 40 especially, make sure you warm up before you do any physical activity. And even if you're not, you probably should warm up before you do any physical activity. Every time I do this, I swear I'm just popping my shoulders every time. Okay, what you got? Yeah, it's like a parent-teacher association, or PTA, in the United States. So like my kids' school has this PTA group that basically is just a whole bunch of people, but they said friends because it's not just parents and teachers. So it also sometimes includes alumni who had either they themselves went to the school or their kids went to the school and now they're out. So right. why don't we run through all of the Tego forms, which are super simple, but at the same time, since I'm like, trying to do black belt when I go back, I'm going to need to remember my basics. So, Tego 1. It is first a left side down block, and then a right punch, and then a right side down block, and then a left punch. I can only shorten my stances in this room. Down block, followed by 3 face-high punches and a kill, which, generally speaking, we're not going to be yelling into this microphone. It just would not go well. Then we have to do a 270 to the left and a down block, and then a right punch, and then a right down block, and a right punch, and a left down block, and 3 face-high punches, and a kill. And then slide left down block, right punch. Ooh, that's a right punch low. Right down block, left punch. Back to Jumbi. Recalling some of these. Nice. Okay. So since it's Tego, these are like super simple ones that we give the kids initially. So Tego 2 is gonna be, again, we start with left down block and a right punch. But it's a face-high punch now, so it's different. Right down block and a face-high punch. Left down block, and we go up block, up block, up block with a keel. Slide left, face-high punch, block, face-high punch, down block, up block, up block, up block. Ow. Oh, wooden blocks. Left down block, face-high punch, right down block, face-high punch, and return. Tego 3 is left side fugal inside out block. So this is the first one where it's like really different. We are about 80% of my weight on my back foot. This was a block that comes from underneath and comes up like this, and it's like the front of your fist is doing the block here, followed by a Jongu low punch, followed by right side. And the other thing that's different about fugal stance is that my back foot is facing basically 45 degrees back, and front foot is facing toward direction of travel, which is usual. But okay, so inside out punch, back to down block to the center, but this time we do a kima stance, which is a horse stance, evenly weighted straddle position. So in the direction of travel, we're going to be facing either front or back. And here, this is a bunch of face-high punches as well. But now we're in this horse stance, kima. Kyo. And 270, or wait a minute. 1, 2, 3. Yeah, okay. So we go from here, come back, down, block again. Wait a minute. Crap. Yeah, it's an inside out. Okay. Phew. All right. And why not do Pinon 5? Or wait, no. That's Pinon. It's not Tego. Yeah, never mind. We'll do that next time. Go through all the Pinons. Right. Back here and... Okay, I didn't switch over the... stuff. It's fine. What do we got? Okay. Was that this D&D game, or not D&D? It was TitansGrave. And our location hosts pulled out a Jim Beam bourbon. I was like, ooh, like that. It was very nice. This one is the Jim Beam Red Label and Honey, I think it is. So it's very nice. Hashtag not sponsored. It's very... Dare I say it smells almost like vanilla extract. How it's like, 55% alcohol and then vanilla bean. Like, that's kind of how it smells. But it's bourbon and honey, so. Dangerously drinkable, so do not have almost any of that. Okay. So yeah, this does not bode well for me. I'm pretty sure I don't understand any of this, but it's all good. It said ordinary differential equations at some point, so I was like, yeah, sure, read through it. We'll see. Estimate of the form for the uniform norm of the difference between the nth Picard approximation and the solution. Okay, so as I understand it, right, you're using a sequence of piecewise linear approximations. This is the Euler method. So we talked about this last time, where basically if you have just like, how many segments do you have? That should be the nth order that you're using, in theory. Basically, your starting point, you take that point, you find the slope of the tangent, i.e. the slope of the value of the differential equation at that particular point. That is now the slope, and then you trace that forward delta x, however far that is. If it's just to b, like a to b, then it's just a linear approximation of one step. And then if you say, I want it in 2 steps, it's going to be from here to here, and then it's going to go from here to here. It doesn't really follow the... Yeah, you can't have... Sorry, we're not finding what b is a priori, right? You could say like what your b value is for x, but you're not finding your d value of y. That just comes out through the Euler's method process. Right, so start at x equals a, find the slope of the line, and then if it's just a one step, then that we're just using that slope wherever we get, that's your b, like b comma f of b. If you're using 2 steps, then again we go, okay, we're going half as far, but along that same slope. Reevaluate the slope here. That's now going to be, let's say, like this. And then we use that same distance to say that the next point is going to be here instead of just there, right? It's now going to be up some. It could also go the other way if it ended up being a lower slope halfway through or whatever. So it all kind of depends on what we got going. But what is the uniform norm of the difference between the nth Picard approximation, so using our n line segments, and the actual solution? So if we were to start at the same point, but we use approximations to get there versus we use the actual differential equation to get there, how far apart are they? Uniform norm, I'm not actually sure what metric that is, but I assume that that is going to be difference of squares within all of the dimensions. So on a two-dimensional plane, you all probably would understand it as just your standard distance formula. Square root of the difference of the square, no, the square of the distance between expected and actual, experimental and actual, and do that for the same, do that the same for all three or all n, nope, don't do n, for your d dimensions. Okay, an application for the contraction mapping principle thus gives a slower convergence rate than the original method of Picard. Indeed, Philip Hartmann, in his classical textbook, gives the Picard-Lindelöf argument only, not mentioning contraction maps at all. So does Vyacheslav Vasilyevich Stepanov in 4. Lev Semenovich Pontryagin in his famous ordinary differential equations 5 gives both Picard-Lindelöf argument and the proof based on the contradiction mapping principle with a geometric rate. The aim of this note is to present the simple observation that a slight refinement in the contraction mapping principle gives a rate of O of alpha to the n over n factorial, namely if we consider a decreasing chain of subspaces and a mapping that takes each of the subspaces of the chain into the next one and contracts more and more on each subsequent subspace. For instance, let H be a complete metric space with metric D. Let H of n, H sub n be contained within H, be a decreasing chain of closed subspaces. So H sub 0 is H superset of H1, superset of H2, superset of, etc., to H sub n, etc. That's sort of Aleph sub n, be a member of 0, 1, and let T, I need to ask what this is. Kappa? What the okay. Sure. You know what? Sure. That's great. That is Kappa. Apparently. Love it. Love that for us. Let kappa sub n be a member of 0 to 1 open, and let T be defined as H to H map satisfying the assumption TH sub n is a subset of h sub n plus 1 for all n greater than or equal to 0. Yeah, okay. Wait. That looks backwards from what we had before. Although T, right? T is going to be the map. Oy. D of, so I'm guessing the distance between Tx and Ty must be less than or equal to kappa sub n distance of xy for all x and y within h sub n and n greater than or equal to 0. The map T has a unique fixed point P. For all x in H, we have the following inequality. Distance between T to the n, right? N mappings of x. Oh, jeez. My whole... Who's it's... The plastic mat here. I've been saying this for a long time. I need the plastic mats with the the grippies in it, but don't know if that was an American thing. Okay. For all x in H, we have the inequality. Distance between T to the nth mapping called T on X to the unique fixed point must be less than or equal to kappa 1 through kappa n plus 1 times the distance. Okay, because we're going to map them each in turn. Distance between x and p. Right, so we're going to get n. And then when we do it again, right, n has changed. N is greater than or equal to 1. Slight modification in the simple scheme. Different metric must be chosen on each h sub n. Provides a proof of existence and uniqueness for ordinary differential equations and yields a precise rate of convergence. We conclude this note for a few brief remarks on the history of proofs of existence and uniqueness theorems from Euler to Cauchy to Picard-Lindelöf, Banach-Caccioppoli. Contraction mapping on a chain of metric spaces. Let a sub n, alpha sub n, greater than 0 be positive constants, and let h sub j, d sub j, where j goes from 0 to infinity, be a decreasing chain of complete metric spaces, h0, superset h1, superset h2, etc., such that the distance sub j between x and y less than or equal to alpha sub j plus 1 d sub j plus 1 times xy. Oof. kappa sub j be greater than 0 be constants, such that the limit of the supremum of alpha sub j kappa sub j is less than 1. What's that stray j doing? I don't know what it is. It's Dr. Gold. Good evening, everybody. Welcome. My name's Obi-Wan Pez. This is Ensign Plex Pachinko, just in case you've never been here before. Currently, we're doing some Math Communication Monday. I'm having some trouble with this because I just do not have the background for it. I mean, I sort of have the background for it, but probably should have paid a little more attention in linear algebra. Senior level, before you ask. Yep, crazy set theory. How you doing? What were you up to? You needed Zach and Jeff to translate? Nice. Anybody who somehow does not know Dr. Gold yet, please give him a follow. He's got all sorts of help streams, both for math and for physics especially. And he's doing all sorts of cool stuff, hanging out in California. Much sunnier than it is here. Doesn't matter where I am, honestly, but I'm in the UK, so it's pretty much a guarantee. Yorkshire, woo! Hey Jade, how's it going? Yep, we're hanging out Leeds adjacent. If anybody else did not have any... nope. Yes, you did have some sunny days here. As did we. Anybody who does not already follow these other awesome streamers, please go ahead and give them a follow at some point. We have Slim from the Academy of Useless Ideas. Dr. Gold just came over from Actual Education. Don Factorial is a good friend and engineer and math tutor. Ian Stuckey does all sorts of high-level math that I will probably never comprehend, and that's okay. They also do dissertation writing at the moment. So trying to finish up, get all that going. E to the 2i pi is Zach. He's been all around this entire area. Thank you so much for the follow. Meriwether Remark does tutorial type streams. Penn Center does a lot of tutorial type stuff, and also is a department chair of mathematics and loves Zelda. So if you want to follow for all of your Zelda content, Penn is the place to go. PhoboStream does all sorts of stuff, including math and coding, and there's some other stuff that I definitely will forget. Physics and Depression kind of does what it says on the tin. Go check him out. He's great. Talos Teaches. I haven't seen Talos in a bit, but they're around. And the Tutor Wizard. And if anybody does study streams, these are people who really love learning stuff and sharing it with the world. So go ahead and check out Rendeo, Math Spellbook, FizzBuzz, Suna O, and Walking Stick Library. I did it again. And check out Matt over at Math Pond. So sorry, Matt. I will change that command one day. It's even open right over here. Chatbot commands. Custom. Math. And Math Font. Ah, crap. I'm out of characters. That's the other problem. We'll figure that out. Anyway, currently we're looking at the contraction mapping on metric spaces of Picard-Lindelöf arguments and Banach-Caccioppoli contraction. So, trying to figure out exactly what this is talking about. Like I said, this is probably a bit above my pay grade, but that's all right. For the most part, I have been teaching math between like basic stuff, generally Algebra 1, and differential equations on the top side, at a community college in Maryland for the last 15 years. Well, that's sort of a lie. I've now been in Yorkshire for basically 2 years, and so it was the 15 years before that. I also do TTRPGs. I do gaming. I don't do TTRPGs on stream. I do some gaming stuff on stream, and I also do martial arts. So I've been working with Tung Sudo, which is a type of Korean family karate, which is the which is the one that Chuck Norris made popular in the United States. I wouldn't say he brought it, but he made it popular. And then I've been working here in the UK on Eskrima, which is a stick weapon martial art, and also Tai Chi. So we've been having some fun. And basically just trying to learn as much as I can before we go back. I essentially have like pseudo-private lessons, but they're not meant to be. He's getting more people in. It's just taking a bit. Okay, so the distance between... Okay, nope, hang on. Let P be a mapping from H0 to H0 with the following properties. P dot times on H sub j is a subset of H sub j plus 1 for all j's. The distance between P of x and P of y is less than or equal to kappa sub j plus 1 d sub j xy. That's the same behavior as all the stuff up above with t. In the application to the Picard-Lindelöf theorem argument, the constant a alpha sub 1 to alpha gives the length of the interval on which the solution is defined. Set h to be the jth mutual intersection of all h sub j's. Okay, so just the intersection of all h sub j's. The map P has a unique fixed point x sub infinity, which belongs to S. Moreover, for all x in H and for all n greater than j, or equal to, the sequence x sub m defined by the following formula. X sub m is equal to P. What in the hell? Yeah, I don't understand where the superscript is coming from in that one. Because we're not... Yep. Not taking the composition of, like, multiple functions. It's like P superscript compose M. Doesn't make any sense. Oh, you know what? It does make sense because if we're using x's, we have to use the nested whatever. Okay. No, that's fine. Whereas when it was just P and H, right, we weren't using composition in order to say like P of H. But we did say that when it was the actual variable of P. Okay. I don't necessarily like it, but it's fine. X sub m is the mth composition of P on X. Okay. Satisfies the relation d sub j of x sub infinity to x sub n is less than or equal to C kappa n, alpha sub n, kappa sub n. Alpha sub n minus 1, kappa sub n minus 1. multiplied together until we get alpha and kappa sub j plus 1 times d sub j of x sub 1 plus j and x sub j. This is quite mean. All right, the series for C converges by the limit of the supremum being less than 1. In particular, if kappa sub n is L over n and alpha 1, alpha 2, etc. to alpha, then setting j equals 0, we obtain d sub 0 of x sub infinity to x sub n is less than or equal to e to the alpha L, all right, come on now, times L alpha raised to the n over n factorial times d sub 0 of x1, x0. I can see some of it. Okay. Proof of the Picard-Lindelöf theorem. We now apply limit and the proof in Dow space R. By the way, right? If anybody wants to follow along, feel free. Allow the space or the dth dimension of reals with the norm v is equal to the square root of the sum of v sub I squared. So that's going to be the difference between the Euler norm and the actual value. Consider the space-time parallelepiped. Nice. And let f be something that maps real to R to real of d dimensions. Be a continuous function satisfying Lipschitz condition y. Let alpha be minimum of a and b over m. As in classical constants, alpha gives length to the interval on which the solution is defined. introduce the Picard operator P by the formula Py of t is equal to y sub 0 plus the integral from t0 to t of f of s comma y of s ds. Differentiating that ends up yielding dy dt is equal to f of t y of t. Cannot simplify presentation by using the induced matrices. Indeed, for the Picard operator, we have the following. Only obtain convergence in the interval with alpha L being less than 1 and only with geometric convergence rate. All right, completeness. One way of checking completeness is to take y0, y1, y2, set and note that. By definition, we have u10, u20 in C from t0 to plus or minus alpha. Completeness of Chebyshev matrix. I've seen that name spelled very differently before. Although I don't know if it's the same person, I guess. Now implies completeness of metric D sub j can also proceed as follows. Check that matrix spaces are complete. Indeed, consider a Cauchy sequence x sub n. The inequality here implies there exists a function Okay, got some stuff talking about the rate of convergence. Differential equations with complex time. Lovely. Holomorphic functions. Okay. Gottfried Wilhelm Leibniz proposed the term differential equation, equatio differentialis, and Leonhard Euler in St. Petersburg obtained the first existence theorems using, in modern terms, the method of approximating the solution by a convergent sequence of piecewise linear functions, the method that bears his name today. Vyacheslav Alexandrovich Dobrovolsky describes the history of existence and uniqueness for ordinary differential equations in the 19th century. Dobrovolsky. Nope, there's no O there. Dobrovolsky conjectures that Augustin Louis Cauchy may have been aware of the existence uniqueness theorem already by 1820. In 1844, the abbot François-Marie Napoleon Moignot published a course in integral calculus based on Cauchy lectures and included a proof of existence using Euler's method in lessons 26 and 27. Moignot gives the sufficient condition that the partial derivative of f with respect to y be continuous and bounded for the existence of solutions for the ordinary differential equation written of the form y prime, dy is equal to f of xy dx. That's how you write a differential equation. Woo! The uniqueness of solutions is briefly mentioned. The extension to a system of ordinary differential equations is treated by Moignon in lesson 39. Again, the uniqueness of solutions is treated very briefly. Existence and uniqueness under Lipschitz condition is due to Rudolf Lipschitz, who again used the Euler condition, Euler method, and cites neither Cauchy nor Moignon. Lipschitz gives a detailed proof for both the existence and uniqueness of solutions and makes the remark that uniqueness need not hold if the Lipschitz equation is not verified, without, however, providing scientific counterexamples. Proceed to a brief review of iteration proofs of existence and uniqueness. Let's recall that solving equations by iterating a contradiction is a procedure with counterparts in antiquity. Heron of Alexandria in Metrica 69 AD uses, in modern terms, the contraction x goes to 1/2 of x plus r over x in order to find the approximate value of the root of r. Very precise approximation of root 2 on the tablet YBC 7289, paleographically dated to the 1st or 2nd millennium BCE, currently owned by Yale Babylonian Collection, has led scholars to the conjecture that the scheme was already in use during Old Babylonian period. What? That's bonkers. I love it. Okay. I think we're probably going to duck out here. So, where are we going? Let's head over to Casey Snow Art. She's been up for about 2.5 hours. Year of the Fire Horse illustration and Sub-Zoo co-working stream. So, we'll be back tomorrow with, I don't know with what. I think we're just doing, at the moment, more blueprints to try to find stuff. But we could try something else. It is going to be short game. Oh, we were doing Level Devil. That was right. So maybe we'll pop back into Level Devil first and see how far we can get in that, and then see where that takes us. So, hope you all have a good night. We'll see you tomorrow, probably for Level Devil, and then we'll be back on Wednesday for more mathy stuff. So if you have any questions on mathy type stuff, bring them back on Wednesday, and I'll be here. So thank you so much, everybody. My name's Obi-Wan Pez. This is N Simplex Pachenko. Catch you next time.